every good things come to an end, and so is the case with IPv4 addresses. Though with the use of NAT and subnetting, the lifespan of IPv4 were enhanced, but at some point of time, the IPv4 address will be completely exhausted, and it has to be replaced with IPv6 in totality. So today we'll discuss about the IPv6 headers. The first thing you require to know that the size of a IPv6 address. The size of a IPv6 address is 128 bits, much bigger than the 32-bit size of IPv4. If you look at the IPv6 header, the IPv6 header is a much simpler header format than the corresponding IPv4. IPv6 designers have removed all the complexities of IPv4 and made a very simpler fixed size header for IPv6. If the IPv6 header is a fixed size of 40 bytes, unlike IPv4, there are no options. It has done away with options. So this is a fixed size header of 40 bytes. Clear? So it's a 40 bytes header, fixed size header, and it has done away with all the complexities. It has removed fragmentation. IPv6 does not allow fragmentation at all. So there are few numbers of header information in IPv6. IPv6 supports something known as extension headers, but these extension headers is not like the options. Extension headers are a part of the payload. If you think of the data, the actual data, so this data and the extension header consists of the payload. The header size is 40 bytes, is a fixed size header. We'll discuss these fields one by one, but I would advise that if you have not gone through the IPv4 headers, please go first with the IPv4 headers, because most of the header fields are almost similar to the IPv4 headers. So we'll not discuss them in detail. We'll simply mention them. We'll simply mention their task. To know the details of certain header fields which are similar in nature with IPv4, you have to refer back to the IPv4 header discussions. So let us start discussing the header fields one by one. The first header field is version of 4 bits. It is similar in nature with the version field of IPv6. This identifies the IP version number. So in this case, it represents the internet version protocol 6. So the value of the version field will always be 0110 in a IPv6 datagram. Remember, simply replacing the value of 6 with a 4 does not make it a IPv4 datagram. In a similar fashion, where the version number of IPv4 header is 4, if you replace it with the number 6, it does not become a IPv6 header, because if you look at it, the datagram format of IPv6 is different from a IPv4 header. So first thing, the IPv4 datagram version field, it contains the number 6. The next field, traffic class, which is of 8 bits, it is almost similar to the TOS field, the type of service field in IPv4. So in this case of 8 bits, 6 bits are provided for priority handling. So these bits are used to indicate that this particular datagram requires a particular type of service. It requires some priority handling, it requires some other service. So this sort of information is provided by these first 6 bits of traffic class. The remaining 2 bits are used for something known as explicit congestion notification. This is an advanced topic, and we'll be discussing about this topic in a different lecture sometimes later on. But understand that out of this 8 bits, 6 bits are used for priority handling and 2 bits are used for ECN or explicit congestion notification. But in spirit, the traffic class is similar to the TOS field in IPv4. Next header field is flow level of 20 bits. A flow is defined as a sequence of packets sent from a host to a destination for which the source desires special handling by the intervening routers. That means flow level is simply an identification of a particular stream of data. Say A and B are in communication and different type of data is flowing from A to B. There may be some text data, there may be some audio video data. So a flow level identifies a particular stream. So if A and B are doing some sort of, say, video chatting or video conferencing. So if A and B are conversing over a video application, then you can think of that 2 different flows of data are going. One is the video flow, the video data, and one is the audio data, whatever data they are speaking. So there is an identification of the audio separately, there is an identification of the video separately. So flow is basically an identification. How so? This flow is uniquely identified by the combination of the source address, the address of A, and a non-zero flow level. That means some number at the flow level header field. If a package do not belong to any flow, it carries a flow level value of 0. Now, what's the basic use of flow level? Is the basic use of flow level is it is used for maintaining quality of service. That means since A and B are say in video communication, there is some minimum requirements of the data flow. So certain amount of bandwidth has to be always there, otherwise the quality of the video talk between them will degrade. So a particular bandwidth has to be managed constantly throughout the duration. So how will the intervening routers know that this particular flow of data requires special handling? How will know that this particular datagrams requires a minimum bandwidth to be maintained? This is ensured by this flow level, but so provided that a particular flow level, the host can tell the intermediate routers that for this particular flow I requires this particular handling because there are certain quality of requirements. So apparently flow level is some form of identification of a particular flow. The next header field, payload length, this simply is used to indicate the amount of payload. If we go back to the header diagram, so this data, what is data? Data is that packet which is coming from the transport layer. So this data, the data that comes from the transport layer plus this extension header. Now extension headers are very rarely used, so you can almost think of the payload as the data that is coming from the transport layer. So the data packets coming from the transport layers are inserted in a IPv6 datagram. These packets, as well as if extension headers are used, they totally are calculated in as the payload. So this payload length indicates the total amount of payload in bytes. So whatever value is there, that number of bytes is the total size of the payload. The header field, next header of size 8 bits, is similar in nature to the upper layer protocol of IPv4. It indicates to which particular upper layer protocol this particular datagram belongs to, whether it belongs to TCP or UDP. So the numbers of TCP and UDP, the number that indicates TCP or UDP is similar as in IPv4. So this next header is the glue between the upper layer and the network layer. Hop limit is completely identical with the TTL field of IPv4. These contents of this TTL field or the hop limit are decremented by 1 by each of the intermediate routers that visits while that datagram flows from the host to the destination. And we have already seen that whenever this field reaches 0, that particular datagram is discarded by the intermediate routers. We have already discussed in the IPv4 header why this TTL field is required to avoid always going through a particular loop. So this hop limit field is similar to the TTL field of IPv4. And after hop limit, the next header fields are the source and destination address. The source and destination address are of 128 bits, unlike IPv4 where the size of the source and destination are 32 bits. The format of IPv6 source and destination address and IPv6 address, how they look like, how they are represented, that we will discuss in a subsequent lecture. So understand that the source address and destination address are of size 128 bits. IPv6 also supports something known as extension headers. Extension headers are additional information, supplementary information that can be used by network devices such as routers, switches, or the endpoint host to decide on additional factor about an IPv6 datagram. So that means if some other information about that particular datagram is required, then they are put into the extension headers. The length of each extension header is an integer multiple of 8 octets. Now remember, extension headers are considered a part of the payload. Now how does the intermediate routers know that extension headers are used? This is done by using the header field next header. So we have already seen that next header field indicates the upper layer protocol. So if I use a particular number, it belongs to UDP. If I use a particular number, it belongs to TCP. If extension headers are used, then a particular number is used which indicates that this datagram is using extension headers. Now there are certain extension headers. Now in this extension header, say different numbers of extension headers can be used. Say I use 3 extension headers. So in the first extension header there will be a next header field. That next header field will indicate the next extension header. Now this next extension header will have another next header field. It will indicate the third extension header. Now in the third extension header, say I use only 3 extension header. In the third extension header, the next header field will indicate the upper layer protocol. This is how the extension headers are used. This finishes our short discussion about IPv6 header format. As you have seen, the header format of IPv6 is much simpler than the IPv4 header. Thank you for today.